Hi, I am Woncheol, and I would like to introduce you how my colleagues and I are working on a method to easily collect and visualize traffic data from the ends. Composite photography, or photostacking, is a technique that captures movement by collecting brightness or darkness in a scene over a time period. This has been a crucial method in an ethologist toolset for a long time, ever since the beginning of the photography. It has helped visualize motions since before we could film a video, and these days it is still providing unique advantages by expressing details that cannot be represented very well in a video. It is also much more storage efficient, so suitable for long-time recording with high quality. Being printable and easily transferable, it is also very convenient for communications. Composite image also summarizes the information very efficiently. Watching a video over many hours is a time-consuming job, and a sped-up version of the video is often unintelligible. But a sequence of composite images can convey the full information of the period very nicely within a short time. But composite photography comes with its own problems. First, in the field conditions, the background is often not ideal. Usually it is just a little bit darker or brighter than the animals, and there are a lot of heterogeneous elements. Second, it is so easy to ruin the entire imagery, especially if it is a long-time recording. Third, unlike videos, it is rather difficult to represent time-segmented information once it is done. So here I present our ongoing improvement for composite photography with modern technologies to maximize their unique advantages and addressing some of its weaknesses. First, we collect maximum or minimum brightness, same as the conventional technique, but at the same time, we also collect average brightness. Then, we make a difference between them and recomposite it to the background again, to have an image that is much easier to interpret. This classical technique, called background subtraction, is nowadays very fast and efficient thanks to modern hardware. Second, we do not collect the entire image at once, but in short segments. Well, at first glance, that seems to betray the whole point of making a composite instead of a video, as we end up with a lot of images difficult to store or handle. But the background does not change much, so we only need to save information about these differences, which is much smaller. Then, with a simple program, we can reconstruct the composite image with any specific time range. Thanks to the small amount of the information saved, it is a much faster and lighter process compared to video editing to do the same job. And thanks to the small amount of additional information, time saved, it is much more convenient and clean process compared to direct editing of a completed composite image. Third, we maintain a small cache of recent image frames captured, as well as a reference frame. Using that, we can respond to uncertainties in the field condition. Wild animals, weathers, falling objects, other people, and many other disturbances can affect the alignment of the device that is taking a long time composite, especially when left unattended in the field. But with a reference frame, we can realign or discard them via SIFT, one of the most popularly used image alignment technique used in these days. But alignment is a very slow and heavy process that we cannot practically align every frame. There comes the cache of the recent images. Using them, there are quick and easy calculations available to detect whether the alignment is locally needed in the first place. So, we can detect an impact event, apply the slow alignment technique only when needed, and then apply post-alignments to segments between those events to save computation resources. And this is the final outcome. Compare the original input and the output. We have a complex background where you cannot clearly see the ends in the original video, with added difficulty of impact and misalignment during filming. The algorithm handled all these issues and they disappeared in the composite image with clean representation of the end traffic. And the result is easily cropped for certain time segments, and even the segments containing the impact does not show any sign of imaging problem. Another use case here shows interspecific competition occurring at a food source, showing different sized species with varying strategies. But we still have to resolve many issues. Although it became many times faster than the naive combination of these technologies, it is still largely unable to catch up the speed of the video stream that is fed into the device. Of course, we can use smaller videos to somewhat address it, but modern behavioral data often needs 4K or full HD resolution, and the infrastructure of the field sites often do not support the high-performance machines. But it is getting faster and faster, and it is already reasonably useful for workflows such as first filming a session and processing that later in the day, or for short sampling bouts at periodic intervals followed by processing time. As relevant technologies are advancing quickly, we envision that a composite photography solution that can be conveniently left in the field, unattended for an entire season, would arrive very soon. With non-stop recording of thousands of hours with high-quality composite images, we would be able to capture a lot of rare behaviors with very little time spent for actual human monitoring of the video. We would like to share this technology with other researchers when it acquires some reasonable level of practicality, and we are interested to see different types of video data that people would want to use this method for. So please feel free to contact us, and we will notify you when a prototype is available or when we find that our method can be applied for your purposes. This work is made possible by Haley Zhou, who helped us collect the field videos in diverse conditions and funds from the National Research Foundation of Korea. Thank you very much.